Hi guys. Today we're doing round 675, and basically that's it. This week should be pretty simple. We have 675 now, and then whatever round's coming up on Wednesday, and then we'll take it from there. Yeah, so I'm gonna update the sub count. I'm pretty sure this number is 2 off, so we actually have 2049, but I can't confirm it, so I'll just leave it as it is. Because whenever I have like a number that ends in 8, it always goes up by a new 10 on the public display. Which means something's off by 2. I'm not sure which, but something is. Anyway, I guess whatever. We'll just live with that discrepancy. And yeah, let's get started with the round. Obsessively checking OBS. Non-degenerate simple quadrilateral. Quadrilateral shape with side lengths equal to A, B, C, and D. Oh, is this some property we need to know? Triangle inequality. So I guess that works. Can show an answer always exists. Okay. I do this just so I can have them sorted, and so because everything's positive, if we just print the last value, then the triangle inequality should still be happy. We just need to make it not too big, I suppose. Yeah. I think that should do it. Do I have some open in Paint? Test cases. I guess this should work. Unless there's some other issue we have with the triangle inequality or whatever. What's with this? Okay, I guess we'll move on. What's happening? How's it hung on pretest 1? Okay, 2 pretests, nice. So there are test cases, matrix. Wants to make the matrix nice if all rows and columns of the matrix are palindromes. Okay, so in any given matrix, like say we have something like this, or we have 4 by 4. That's not a square, I'm sorry, but that's what we got. Then this element has to be equal to this element, and this element for the rows to be for the rows and columns to be palindromes. Similarly, this has to be here, and these all must be symmetric, and so on. So because we can increase or decrease. Okay. Does that help? Well, we just need to make all of them equal, and so we can, because this is small, we can just kind of like try all possible ones and then see, I suppose. Yeah, I guess that should be fine. Okay. problem, but so we're going to iterate only to the first corner of the matrix, or the first like upper left corner, because they're all equivalent. Jeez, my typing is going to be weak because it's like really kind of cold here. So my hands are freezing as always. It's kind of a weird implementation. Values.push back mat ij. If I is not equal to m minus 1 minus I, the opposite element, values.push back mat m minus. We can do the same thing with j. If j is not equal to m minus 1 minus j, then values.push back I and then m minus 1 minus j. And we can do the same thing, but now for the both of them, then values.push back the opposite of both of them. What's the bounds? 10 to the 9th, so it's 4, just 1e10, x, e, so basically just trying all possible values and then summing them up for all groups of 4. I guess that's what they want. What? What? Misspelled comp. 8 and 42. Okay, I guess that's it. So here we go up to the halves. Let's try a odd matrix. Where's test case? So for example, I have 3, 3, or 1, 3, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. And that should take, this should go to 5, so it'll be 1, 5. So it'll be 12 plus, these will be equal, so 2, these will be equal, so 6. So 20, I think. Okay. Guess that works well enough. Okay. Probably a smoother way to do that, but whatever. Oh my god. Big numbers. Sometimes it's not easy to come to an agreement and a bargain. Right now, Sasha and Bobo can't come to an agreement. Sasha names a price as high as possible, then Bobo wants to remove as many digits in the price as possible. Name some integer price n. The sum of all possible. Seriously? Or removes a non-empty substring of consecutive digits. The remaining digits close the gap and the resulting integer is the price. Alright, here's the idea. I guess we're just gonna do this out. So let's say we have some number like 4, 7, 1, 2, 3. We're going to basically convolva remove no digits. non-empty. Why did they like exclude the... Oh, that's annoying. Come on. I guess that's fine. Okay, say we're gonna like do all subarrays starting from a fixed left point. So say we start here. Then this value is like something. And this value is something else. So we're gonna start by like assuming we remove everything. Then this value is just whatever it is. But then now what happens when we change the right endpoint to here? Then this value gets multiplied by 10 because now we have 473, and of course we get the 3. And so when we move this over here, this value gets multiplied by 10 again, and this value is now 23. And then when we move this here, that's empty, so we can't do that. Okay, I guess that's it. C into S. LL ants equals 0. Do we have test cases? We do not. Okay. So now I'm going to... How's this going to work? I guess we'll start the left endpoint from the beginning. 4L equals... Wait, is the beginning or end easier here? Whatever, it doesn't matter. So I'm going to store a variable for the left side. Left side equals 10 times left side plus SI minus 0. That gives us the value of the digit from the string. And what this left side does is it's basically just going to like keep constructing the number iteratively. That is, when we stick on a 1, this 47 gains 10 times its value, and we add the 1. So then LO right side for LO j equals n minus 1. J is strictly greater than I because we can't erase nothing. Oh wait, ants equals ants plus left side mod mod. And this should also be mod mod. Everything is mod mod, and the mod is 10 to the 9th plus 7, I hope. Yeah. Okay, now this should also be right side. So I guess we right side equals... How does this work? Oh, we need a power of 10. Right side plus Sj minus O times the power of 10 mod mod. How do I keep typing right size? I don't understand. Okay, now both left side and right side are multiplied by power of 10. So ants equals ants plus left side times P10 plus right side mod mod. I suppose that's it. Just kind of do that and that. Oh, come on. What am I doing? How do I keep typing size instead of side? Like, the letters aren't even close. That doesn't even make sense. Test cases. Zero. Nice. Okay. Because n doesn't exist. We should like vote for some standard for if we like either give n as a specific value or force us to derive it from the... Still didn't compile. What? Ah, jeez. Slow day for me today. Okay, what? How's it 349? Because we're counting the left side 3 times. I guess this should be n minus 1. How does that work? Oh wait, this should be, wait, should it? What's happening here? Something's being messed up. I guess this should go to only I plus 1 because otherwise we're like doing some overcounting here. Still messed up though. Alright, what the hell? Okay, so we fix the, let's do it for 107. So right here, we fix the left endpoint to be here, meaning we include this number. That's what we want, right? I guess we can have this be there too. This is messy. Okay, so I guess the first left side is here, and then we have nothing here, but or the first split point is here, which means we're going to start removing these, this, and this. And so we check all those three, and I guess now we can do is greater than I. Is that right? Right now I is 0. But j should be at most this. So it should be greater than I. Wait. Oh, I'm so confused. Why did they do this to me? I don't actually know. Okay, that works. Alright, so I guess now we can make it be up to I because j equals 1, which would be here, is allowed because now I is the position here. So I is going to be one of these, and then j is going to be the right endpoint of the substring we removed. That is so annoying. I'm going to have to figure this out later when I explain it. Why is it hanging on pretest 5? Oh, come on. Okay, I'm turning home. TLE. Wait, what? How did I get to the point of submitting this without realizing this was n squared? What the hell? Jesus Christ. I actually don't understand how I got to the point of submitting this without realizing this was n squared. I mean, okay, obviously all of this is optimizable. Like, we can... Jesus. Yeah, okay, so say we have some I fixed, then we have 3 possible values for j. All of these right things are some suffix, and what that means is we can do like suffix sums, I guess. So, and then we just kind of optimize the left side in a similar way. I honestly have no idea how I got to the point of submitting that without realizing it was n squared. Kind of scared of what's to come if I'm doing stuff like this. So we can do this whole thing like right now, where suff j equals cur suff. So again, this is kind of like a suffix sum. And then we can do like a different sum of powers of 10. basically, here's the idea. We'll do the left side and right side independently. So let's say we have here. Then we want to sum the right side we get from removing this, which is 0. The right side we get from removing this, which is 1. And the right side we get from removing this, which is also this. And so this value will be stored in suffix of I plus 1, I guess. So if I is less than I minus 1, ants equals ants plus suff I plus 1. I'm actually so confused. That must be like square that equal to 0. $11.42. Maybe we like switch the order of doing this. I guess that's how we have to do it, because on the first operation we don't have a left side, which kind of makes sense. 132. That makes even more sense. Let's check what's wrong, I suppose. $27, $114, $121. Okay, that's fine because we don't need to use both of those. So the problem is on the left side then? Okay, so the right sides are going to contribute 28 in total. And the left side is going to be 1 and something's messed up here. No, these are going to contribute 21 in total, and then the left side should also be 21, but somehow it's way higher than it should be. 10 times left side plus SI minus 0. I think we're messing up the powers of 10. Yeah, okay. So we have to like do this backwards again. Nope, let's not do that. We're just gonna like compute the powers of 10 in the same way, I guess. Suff P10. So at the point of this, either we remove the whole thing or we don't do anything, so this power of 10 should be 1. But then when we're here, we can either do this, in which case we get 1 times this, or we can do this and then we get 10 to the 1. Or we can do this, and then we get 1 plus 10 to the 1 plus 10 to the 2. So the suffix of I should be plus 10. That should be sum. That should be sum. What the hell is going on? J, right? So that, I guess, does exactly what we want. Oh yeah, forgot to fill in that index. That was stupid. That was very stupid. That was incredibly stupid, honestly. I don't know what the hell that was. It's like kind of surreal. Blame the code. Okay. Long for some time already. When I return home, needs to get home as fast as possible. So they're instant movement locations. This area is a city of n times n square blocks. Let's move from the block with some coordinates to other coordinates. Also, there are m instant movement locations in the city. Their coordinates are known to you, and you can move to an instant movement location at no time if it's in the same x or same y as the location. So you can go there, but not go anywhere from there. Do they guarantee that these locations have different x or y coordinates? No, they don't. Why would they? Just read these in. So I mean, okay. So clearly there's no reason to ever return to a location, so you'll visit each location at most once. And I guess consider the location you end at. If you end at some location, then the final distance is the time it takes you to get to that location. Yeah. So I guess it's some kind of weird like Dijkstra's algorithm where we find the shortest time it takes for us to get to any location, and then either our final path will go to like say we have a bunch of locations like this, I don't know, wherever, and then our ending location is here, then our final path will either go from like some location to this or just directly to this. And of course it doesn't necessarily have to be like, we can do the wobbly thing where we go to the locations and then do that or whatever, where wobbly is teleportation. I don't know, it's kind of weird. Yeah, that's a possibility. So we move out. Okay, so movement costs no time, right? Going to a location moves it costs no time. Okay. So I suppose there's some stuff going on with okay, so imagine drawing these lines. I'm gonna move this down and imagine drawing these lines out like so. Like these are the movement lines. Just gonna assume these are different. Alright, okay. Now let's say we want to get from here to this y coordinate. Or for example, this y coordinate. Or it's, this x coordinate so we can get to this location. Then it's fine for us to go to this, jump up here, and then do that, because that's not going to affect our x coordinate, like this y movement up here. And in the same fashion, if we want to get down to here, then it's okay for us to go here, jump to here, and then go here, jump to here, and then go here and jump to here. Which means that no matter where we're trying to get, I think it's optimal, or there's an optimal strategy where every movement we get either takes us to the final location or goes to one of the nearest two coordinates. I think that's how it works. And so therefore, I mean, one of the nearest two, the nearest two jump locations in one of the x or y coordinates. So therefore, in some sort of graph fashion, we only need to create an edge from this to the nearest two in the x direction and the nearest two in the y direction. And obviously the cost is just the x distance or y distance. And for good measure, it can't hurt to just add an edge from the initial thing to all of the jump positions, because it's just implementation, makes implementation easy. So I'm gonna, okay, whatever. Sx, sy, ex, fx, fy. Hopefully I don't submit an n squared for this. I think that's a great idea to not do that. Okay, now I'm just gonna whip out my Dijkstra template because I can, and it makes nope, not that. It makes everything easy. Don't have test cases. Okay, right. We do not. D dot init n or m, not n. So now we should also have indices here. Pair. So the first pair is going to represent the position, and then the second is the index. It's a great idea to not switch up n and m, although hopefully this sample should make sure that doesn't happen. So we're also going to just assume that the start has index m because, oh no, why not? So d dot edge m, it should be directed edges. Actually, it's not directed, I guess. Doesn't really matter. Time limit is 2 seconds. We can afford a few extra. Abs sx minus fx plus abs sy minus fy. So then we add an edge from the start point to every jump position. Actually, they should not be directed. Actually, no, they should be directed because we can't go back from the start point to the beginning that easily. Yeah, it doesn't matter anyway. Like, there's no reason to go backwards. D dot edge m I, and then the weight is abs sx minus pi dot first, which is x. And we do the same thing for y. We might as well do the same thing for the endpoint because we can. Wait, so m plus 1 fx plus 1 fy. Okay. And then we sort them by x. And now we can add an edge between each one that has neighboring x. D dot edge pi minus 1 dot second. No, an edge from pi, their index, because we need to like preserve that. And then pi and we duplicate this. If I is less than m minus 1. Alright, this should be dot first because this is x distance. And then this is I plus 1. Yeah. And then now we do the same thing for y, except now we have to switch the x and y coordinates when we sort. We can just do that by swapping them directly. And this should be m. Should all be m. N is like almost useless actually. What's the point of n? I don't think there's any reason to include n. Why don't they just make it 10 to the 9th? No word only. Is that the only place where we use it? Okay, good. So now this should be based on y coordinates. Then d dot run from m. C out d dot dists m plus 1. Yeah, that's my Dijkstra template. Makes everything really easy. Or not. Because we need parentheses here. Somehow I always manage to screw that up. Come on. What the hell? Oh, we need f dot f dot f dot f dot f. Yep, because all of these are not the indices. They're just the locations. 8. Nice. How are we on this one? 83. Okay. Well, that's terrible. What? Oh, wait. That seems wrong. Yeah, because we... Because we can't jump from the end. The end is not necessarily a jump point, I guess. but that doesn't make sense why it would make the answer worse. So now I'm very confused. Oh, this should be I n plus 1. Whoops. Let's see, do we do the rest of these right? Okay, so yeah, let's just check. So this is an edge from the start point to each jump point with the cost being the x and y distance. Then this is an edge from the jump point to the end point with the cost being Manhattan distance. This is an edge from the jump point to its previous in x and the next in x based on the x distances. Then we sort by y. Then we do the same thing but for y, and then we run it and we print the distance. Okay. 5, 42. Alright. We have in the overflow issues, stack series is long. Guess we're fine. Do we have time limit issues? It's also a question. Okay. Got that. How are we doing right now? Imagine we don't have the best penalty, but not doing terribly. So yeah, the basic idea is that for any endpoint, it's optimal to, like, there's an optimal solution where you can just, like, get away with just going to the nearest in terms of x and the nearest in terms of y, which is just fine. Pretty sure this is a common theme that's been seen before, but I don't really know. Actually, I've definitely seen something like this where it's that kind of same idea. Okay, I assume we can get rid of the Dijkstra template. This is not going terribly. How are other people doing? We have Monogon trying F. Nice. Okay. String problem. Entertaining string S consisting of lowercase English letters. Immediately developed a unique algorithm for the string and shared it with you. So an arbitrary, possibly 0 number of pairs on positions I plus 1 adjacent. Okay. For each pair, the adjacency, the inequality, yeah. Sure. There is no index that is contained in more than one pair. So what that means is you can only remove an even number of characters at a time. You have to do it on the suffix. Oh god. Seriously? What is this output? But I assume people are solving this, so now we have to as well. How many people have solved this? 20? Doesn't match the leaderboard, but whatever. Mess up, wrong answer. Okay. So lexicographically smallest, which they don't define, is, I guess, empty string is the best. So you solve it for like the full string, and then you remove the first character and solve it then, and then remove the first character again and solve it then. Okay, so how do we... Are we supposed to somehow exploit this weird output format? Oh wait, you can only do it once. Okay. I guess that's better then. I thought you'd be able to do it like multiple times and the string to come together. There are problems like that. Those are... I don't like those. So I guess essentially you only want to remove some character if removing it will lead to you having a better character later on. And actually we don't need that. We just need any letter that's like... Let's get capital letters. Okay, 65. So 65 is less than lowercase, which is cool. Okay, at least these guys are consistent with how they define how they give the length of a string. They just don't. Which, I mean, not giving it is fine. It's just the fact that like every other contest alternates between giving the length of the string explicitly and making you find it yourself. So let's assume we solve for the whole string. Then, or maybe we can solve for it backwards, where we can like dex or random access, which is cool. Okay, well, let's try this. I guess we can use a deck. Or maybe a... No, we want random access, so deck is fine. Then 4 li equals n minus 1. String res. What's the bound on end? 2005. Okay. Now, car best equals that, which means now we can, technically it would be space, because space, if we assume that like we stick on a space at the end of all these characters and space is lexicographically less than a, then the best thing is an empty string, and that's optimal. So we can kind of consider it like that. So if a string is less than some other string and the prefix of the size of the smaller string is equal, then that's kind of chill. So car last. How's this gonna work? I guess I can assume this is in this string. Then, okay, now you to push front SI. It's kind of weird to handle. So if SI is equal to something, let's see, if SI is less than best, then best equals SI, else, or if it's less than or equal to best, I guess, then we can kind of just ignore it. I guess less than best is better, because if we have, say, A versus A, that's A is better. So we want, if there are ties, I guess we want the shortest string possible. So now if SI is equal to the last character, then like what? If SI is equal to last, then we assume best is better than SI. So we do like, I guess maybe we move this here. It's just casework, I suppose. SI is equal to last, then it's better to remove last, so dq.pop front. Otherwise, SI is not equal to last, then how does this work? Like, we don't necessarily want to get rid of best. So if last is the best character, then we can just keep on going. Otherwise, last is, I guess, worse than the best character, which means that Now I said, how does this work? Otherwise, we're not right before the best character. Meaning that there are two characters that are unequal. So for example, say we have this, and then this is the previous one, and now we have some other character, like, wait. So this is equal to best. So either, okay, let's think of it like this. So the previous character is C, the best character is B. We have some stuff going on right here, but we don't care at this point because we're already done with that. So there are three cases. Either this is equal to that, in which case you can remove this. It's worse, in which case we can't do anything. And now last becomes the new best character. Or whichever is better out of these two. And maybe this is better than this, then this becomes the new best, but we already handled that. And then this is equal to best, in which case, same case as this. So it's like dq.push front si, or best equals min best, no, min si dq.front. That's kind of the case we're at, I think. And dq.push front si. Again, that's when si is not better than best, but it's greater than or equal to the last one. Or it's not equal to the last one. Then last equals si. Now we handle the weird output. So ai equals dq.size minus 1 because we have the extra a at the end. Then if ai is less than or equal to 10, ants plus equals s dqi. Else dq ai minus 1 res I equals ai. I don't trust this to work, but oh my god. Yeah, DQ. Let's just call it that, because that's what I expected it to be, and then I violated my own convention. We didn't print the string at all. What? Why? Oh, it should be ants. Whoops. So we're getting the lengths right. Is this right too? Not at all. Doesn't make sense. Oh, we don't want to remove best, I guess. Yeah, we don't want to remove the best one. Maybe that will fix us. 14. A, B, B, C. Huh. Okay, let's fix this one first. Something's going wrong with how we're constructing the string. Don't really understand how. Car. What? How? Why is that not working then? Oh. Whoops. That's kind of weird. Yeah. J. 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 So it'll work for the big ones, but not the small ones. Okay, so now we just have to figure out what's going on with this. We're getting like many of them right, but not the best ones. AAD 40. So EAAD F dot 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 TW. Dead DD. Okay. So 13 is the first one where we have a problem. And somehow E is best. And so we remove DD. And the reason is unknown. If SI. Oh. So we need to update best end here too. So if SI is less than, we prefer best to be earlier, which means you can possibly remove more. So if SI is less than DQ.front, best end equals. Oh boy. Okay, so we need another deck for indices. In.push. Yay, love implementation. DQ in.push front I. So then this is in.pop front. Best end equals in.front. Else best end equals I. Then we can keep that and in.push front I. So every time we do DQ, we also modify end. Guess that's fine. So now do we get the right lengths? No, we do not. And somehow that's because of something. So SI is not equal to last. SI is less than DQ.front. So when we get here, either I plus 1 is equal to best end or SI is different from last. In either case, we want to make best later. Oh wait, this should be, we kind of reversed these. This should be best end equals I, and this should be best end equals in.front. Now we get 16. So what are the actual strings? Here we have A, B, B, C, D, E. Why do we remove the D? So I guess we also need a flag for if in this current string we're forced to have anything worse. And if so, then we don't want to remove unless it makes us better. What's with that? Okay, time for another deck. Let's go. This one's gonna store the worst, like it's the suffix maximum of the current string we have. So worst.push front max worst.front SI. Technically all these can be stacks, but for the end I need the random access, so that's why I use dex. Still need to handle equality especially. So I think we can copy this if statement and base it off of worst. So if worst is true, that means we don't want to remove equals. Which means if worst is false, then yeah, if worst is true, then we don't want to remove equals. And then do the same thing here. Does this even compile? No, it doesn't. If, oh wait. If, what should it be? SI is less than or equal to worst.front. No, SI is greater than or equal to worst.front. Which means if we remove this, it's going to mean that all of the later characters are going to be better. We finally get this? We do not. We still do not. The problem is we don't want to remove this D. I don't understand. What is worst here? Well, we still have this E, which means we're somehow doing this badly. SI. So when we get to the point of removing these two D's, can only choose, yeah, good clarification actually. Even though that's like clear in the statement, I misread it myself, that's still, I guess, good to point out. So the problem is that we get 3 Ds in a row here, and therefore okay, so the problem is here, I think. And SI is greater than or equal to worst.front. Once we make that decision, then it's still wrong. I'm doing this wrong again. It's not the worst. I'm continuously doing this wrong. It's not the worst that we base this decision off. It's like something else. I guess it's the next immediate character. Wait, is this just checking like... if this is better than best? Is that what we're checking here? It's not. Somehow we still remove this. What is best at this point? That I don't understand. What is best here? Oh, this is so messy. See what's wrong, I don't know how to fix it. So the problem here is that this best is D, which means, like, right now the problem is we have D, 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 and E. And my program is choosing to remove this, which will make the string DE, and therefore worse. There's so much stuff going on here. I guess this is also required. Will that make everything still worse? It might. Indeed it does. Okay. That's so annoying. I think I've set this whole thing wrong up from the start. So if best end is here, that means the immediate next character is worse. Which means that maybe the right condition here is that it has to be strictly greater than best. But that still wouldn't make sense, I guess? Or would it? I think it wouldn't. Like, we would have some problems with, like just A, B, B. So at the beginning, best is very small, so SI will always be strictly greater than best. And later on, see, yeah, that's just it. I don't know at this point. So it's going to pass samples ABC, BC, C, space, D. A, B, B, C, D, B, B, C, D, D, B, C, D, D, C, D, D, E, D, D, A, D, A, D, A, D, E, A, D, F, A, D, D, F, D, 40, 40, RD, 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 T, Y. So let's see what we're doing. We initially put DQ and into here. Does this break anything? It does not. Okay. Do we even need worst is another question. And so the only reason we use worst is here. And I think we don't actually want that. Do care. Do we care? Well, so if we have DDD, so say we're trying to figure out where to put best in among these two characters, or these three characters. I guess since we aren't going to remove it, we might as well put it here, which means that we can actually get rid of this condition and just say that if SI is less than or equal to DQ.front, then we make I the earlier one. Otherwise, it's going to be weird, I think. Yeah, that seems right. Does that break our sample? I feel like it also doesn't make a difference because we fixed the logic, kind of. Obviously, we can get rid of this debug printing. So let's see. 4 backwards in the string. If SI is less than the best we have, then make this the best, because now we have a new best. Set the best index, and get rid of worst, because we never use it anymore. Set the best index, then push that and the index to the beginning. Otherwise, there are two cases. If this is equal to the previous one and removing this will get us a better string later on, then do it. Otherwise, don't. And I go to best end, and SI is less than best. Otherwise, we set best to the minimum one of the two characters we have at the beginning. and continue. I don't know if it's right. I think we're doing this right, at least. This is the first 10 characters, otherwise the first 5, then ... then the last 2. And we print the final thing. The bounds are 100,005, or 100,000, sure. Nice. Passed a lot of pretests though. I guess now we figure this out. Okay, what's with this? Does this work? Wait, oh, we didn't recompile. So that is indeed the best thing to do. If we have A, B, 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 A. What? Oh wait, I didn't update last. Oh, so this should be I guess this should be last equals dq.front, right? Jesus, how do we pass with that bug? Because now I'm thinking B equals A somehow. B, A, A, B, A. Yeah, okay. Because when we remove a character, we'll still think last is B. So then I will think I'll think this B is equal to this, even though this last should be A, it's actually B, which is a problem. Stupid. Is everything else still right? Yeah, ADF 10, 9, 8, 9, 8, 7, 6, 5, 6. Okay. That's stupid. Anything else? This makes sense. That, yeah. This is just computing the answer. Okay. Well, that's that. Now we have F. Someone got hacked? Whoa. Whack. And second thread is, as usual, doing well. How many people solved F? We have 10 solves in total, and 3 at the top. We're kind of just chilling down here. Are there people who have solved? Okay, so there are some weird scores over here. I guess this guy will be beating me later on because he can get almost 1,000 more points. Okay, in that case, we're going for F. Or we're going to try and probably struggle with it. And we still have Dexter here. Quite ordinary and boring array A of length n. You think there's something more boring than that, but Elotic doesn't agree. In order to make the array even more boring, it makes Q boring queries. Each query consists of 2 integers x and y. So it's online. Okay, online queries. And whatever the last answer is. Okay, so used to compute the LCM on the segment LR of the initial array A, modulo 10 to the 9th plus 7. Cool. So AI is 2 times 10 to the 5th. Which means things are going to be big. and the time limit's not the friendliest. But AI is small. That's an important thing to note. What reason do they have to block offline? Okay. So first of all, we can think about LCM in a more sort of easy way to think about. Let's say all numbers are multiples of 2 and 3. So we have one number like 2 to the 7th, 3 to the 5. We have another number 2 to the 2, 3 to the 1. Another number 2 to the 1, 3 to the 100, and so on. Then a number that all these numbers are divisible by must be both a multiple of all the 2's and a multiple of all the 3's. And so it just ends up being the maximum over all of the powers of 2, so 2 to the 7th, and the maximum over all of the like exponents of 3, or the exponents of 2 and the exponents of 3. So we get 2 to the 7th times 3 to the 100. So problem is maximum is not easy, because maximum always requires some sort of log factor. Wait. This time limit's not bad. I think I have an idea. So for overall pi function, how many primes are there less than 2 times 10 to the 5th? Calculator. So we need 200,000. 17,000. Okay, that's kind of tight. Does that work? Can we squeeze that? Not sure if we can. That's kind of a lot. We did some weird like square decomp on primes or something. Square decomp on primes would indeed be very weird. What's the status on this? How are people doing? So there's a lot of TLE. 529, 717, 420. Not many pretests. Let's look at accepteds. Wow, that's a lot. Okay, so there's a higher memory limit here than all the other problems, and a higher time limit. Okay, that guy is absolutely going to fail system tests for sure. Maybe not the other guys, but this guy is definitely going to. How goes the rest? Okay, I guess except for F, these ranks are set in stone. Did Monogon ever get F? He has not. He just started going forwards from A and B. Nice. Still a hack on E. So maybe the pretests are... How many pretests were there? I don't think that many. Yeah, 14. For no multi-tests, I feel like there should be more pretests on that one. But anyway, whatever. I still don't know if my solution is correct. It very well might not be. Which would not be a good thing. But who knows? What was D? D was the... Oh yeah, that one. Okay. So queries are online, which... How much memory is... Okay, that's way too much. Yeah. Memory, in terms of memory, that's not gonna work. I didn't even consider memory, actually. The basic idea of those is that there like aren't that many big primes. Like the highest power of 2 is like log 2n or something. Highest power of 3 is log 3 AI. Or power of 2 is log 3 AI. Highest power of 5 is log 5 AI. And like soon enough, when you get to square root AI, all of the primes bigger than that are going to be either zeros or ones. Which means that what happens for those primes? Like either you have it or you don't. It's kind of the way that works. So it's like a bit mask. Don't tell me that's what you need to do. There's no way that's what you need to do. Can't be. I see what I think is a terrible solution to this problem. But it should theoretically work. It's just terrible. You know what? I don't have a better idea. Let's just go for it. So, alright, consider, what's a good bound? Square root 2e5. Let's just go with 500. So consider all the primes less than or equal to 500. Then, in that case, we can kind of do this like RMQ thing, where it's just like fine. So how many primes are there less than or equal to 500? What we want is this again. We want 500. Shouldn't be that many. So 95. Which means yeah, 95. So you could make it use all that memory in total, but of defeats the purpose. This is honestly so stupid, what I'm thinking. But okay, consider all 95 of the primes less than or equal to 500. Then what I'm thinking is we can like build a we can build a segment tree over all of these primes and be happy, because we can build a segment tree over all of these primes and be happy, because then we can do whatever we want. Build a segment tree, sparse table, whatever, some sort of RMQ structure, and then we can there's no way this is going to work. I just don't believe this is going to work. 3 seconds, 512 megabytes, there's just no way. But for the 95 primes, we build a segment tree over all of them, and then we kind of like compute them individually. So for example, for 2, we query the segment tree of 2's, and we query the maximum power of 2 that we have. For 3's, for 4's, for 5's, etc., and so on. So that's cool, but what about the bigger primes? So all the primes that are greater than 500. And I say to you, for that, all of these primes are either 1s or 0s. And what is this? So what is pi of 200,000? There are 17,984. 17,984 over 15 is 1,200. So 15 to 15 times 1,200. That's fine. Is this fine? It's definitely not fine. No, it doesn't work. Okay, never mind. That's stupid. My idea was you can like build a segment tree, but like group all of the k primes together into like one bit mask, since they're all 0s or 1s. And then for like kind of like a bit set, you can do it like that, but that's just so weird. I don't think it would work anyway. There are just too many primes to deal with. Because it would be like, you would get the the number of primes less than or equal to n is like somewhere around n over log n. So you would have an n squared over log n solution, because the bit mask cuts it down by a log, but then the segment tree or sparse table adds a log to memory. So you still have n squared over log n in either time or memory. In either case, it's just too much. Like, it's just going to kill you. And you can't use a bigger value than, say, 15, because you also need to get the wait. No. I just gotta stop pursuing this idea. This is so stupid. This is the intended solution. I'm gonna be mad, because there's no, like, these bounds are so suspicious for that. just no way that can be the solution. But 2995 milliseconds. And some of these solutions use a lot of memory, but like, it's just too much memory. It's like 18,000 over 60 times some log, like 20. So you get 6,000. And no matter what, there's going to be some log. Even if you compress coordinates so there's only O of n memory, and like there's always going to be some log. And 3 times 10 to the 7th. I don't know, does it work? I really hope this isn't the intended solution. Because these bounds are just so suspicious. Like if they had made the memory limit like a gigabyte or something, that would be... What's the exact amount of memory we use? So we okay, of course we don't, in 17 minutes I can't implement all of this, but what's the memory we use? In this case, it's the memory in total, if we compress coordinates, is only O of n. Because the fact that each prime only shows up one time, it means each big number is only going to have at most one of these big primes. And so the number of big primes we have in total is only O of n. So the total size of all of the RMQ structures we use is also going to be at most O of n. And what else is new? So memory's fine. Now we need to deal with time somehow. And the problem of compressing the coordinates is that it's just so stupid. That's the thing. Okay, so 18,000 over 15 is 1,200, which multiplied by 100,000 is 10 to the 8th, which alone will pass, but it's not just 1,200. There's also, for example, the overhead you get from doing coordinate compression and just other things in general. Maybe it does pass. I don't know. So the small primes, the complexity is like, or the, not necessarily the complexity, but like the time usage is, say, O of 10 to the 7th, because you have 10 to the 5th times almost 100 primes. 10 to the 7th times like log of n, I guess, which maybe passes, but is very suspicious, and actually it probably just won't pass at all. And in the other case, you have, for the big primes, you have O of 2 times 10 to the 5th. Divided by, actually it's like 18,000. That's how many primes you have, approximately. 18,000 times n over 15, or 18,000 over 15 times n times, I don't know what it's multiplied by. It's like something like, it's like the sum of, it's the sum of x log x, where x is the sides of each prime group. And I think at x equals square root n, you can make it so this is square root n times square root n log square root n, which is just n log n. So actually, I'm pretty sure that this doesn't even help the complexity. On both sides, it just falls on its face terribly. How is this doing? Okay. Well, F has more solves, but still not that many. Well, people are still being hacked. Whack. Oh, we got F. Jeez. What was the time usage? So 1092. Okay. There's no way this works. There's some other solution or something. But in 13 minutes, I don't trust myself to find it, and it's like there's absolutely no way I can implement it, even if so. So I think I'm just gonna leave it at that, and we'll go over A to E right now. Okay, let's do solutions for the ones I tentatively solved. There is a chance I didn't actually solve E. I might fail system tests and or be hacked. Is anyone in my room a hacker? No one's even tried. So there's not that many people in my room. I guess that's just a thing. So maybe you'll be hacked. I don't know myself. It's a possibility. But, you know, maybe it won't. It's also a possibility. Maybe we can try to hack. I don't know at this point. I'll just do my solutions. Okay, so yeah, alright, here's A. So basically you're given 3 sides of a quadrilateral, and you need to pick any length of the 4th side so that you can make a quadrilateral out of those sides. And it's not necessarily like a rectangle or anything. And it has to be an integer, but it doesn't really matter. So if you've ever heard of the triangle inequality, it's basically that if this is A and this is B, the length of C can't be too big. That is, if the length of C is like so big that you can't even stretch A and B out to make that triangle complete, then it's not possible. And so this condition ends up being that whatever C is, C must be less than, strictly less than A plus B. If C equals A plus B, then you'll have a straight line because you'll only barely be able to make it, and that's not a triangle. So, can't draw a straight line, but that's essentially it. But what I looked up in the beginning is that this triangle inequality extends to all quadrilaterals. So for example, say you have A, B, C, D. Without like loss of generality or anything, D must be strictly less than A plus B plus C. And this must hold for all the other ones. A must be less than the others, B must be less than the others, C must be less than the others. So right now we're given A, B, and C. And because there are 3 sides, we don't actually know that these conditions are going to hold. So we need to choose some value of D such that this holds, but also the other 4 must also hold, which isn't necessarily true right now. So how do we do this? Well, consider like the longest length. Actually, there are a lot of strategies we can do, I guess, but consider the longest length. Like let, even though it doesn't match the picture, again, without loss of generality, let A be less than or equal to B be less than or equal to C. Then automatically A is less than B plus C, because both of these are bigger than it. And B is less than C plus A, or A plus C, because both numbers have to be positive. Like, even if b is equal to c, a has to be at least 1, so that works out. So the only conditions we need to satisfy are that d is less than a plus b plus c, and c is less than a plus b plus d. Straight away, we know these are positive. So this is greater than 0, and this is also greater than 0. So now we need to satisfy both of these equations at once. And that means we can't have d be too big because otherwise this may not be true. And we can't have c be too big because this may not be true. But because both of these are positive, what we can just do is make c equal to d. And that way we get d is less than a positive number plus a number that's equal to it, which is true. And the same goes for c. So no matter what, if we let c equals d, then that is going to be true. So the final answer you can just print is the maximum of the input values, a, b, and c. Because that will make it so all the triangle inequality properties are satisfied. And of course, these aren't necessarily the input values. These are just 3 values that like if you sort the input, then you'll get these numbers. But the final answer is not necessarily the third number. It's just the maximum of the 3 numbers. Okay, that is A. Let's do B. Okay, so for B, let's consider some matrix. We'll assume they're both even, and then we can like do out the casework later. It's kind of the same thing. Okay, say this number is like 5. Then say this number is going to be 5 in the final matrix. Or, yeah, let's just say x, I guess. Then for it to be a palindrome, this must be equal to this. This is the definition given in the statement. So this also has to be x. And then this must be equal to this because rows and columns must be palindromes. So this is also given in the statement. And this and this must be equal to this. So clearly by overkill, this is equal to x. So whatever the final value of this is going to be, the other 3 values in like the corresponding things it has to match with also have to be equal to that. And note that these don't have to match with anything else. So this problem is independent of all of the other problems, kind of. So now we need to make these 4 equal. And in a similar manner, we need to make these 4 equal. And we need to make these 4 equal. And we need to make these 4 equal. If we have like an even number, or if we have an odd number of rows or columns, for example, then it just kind of makes it easier. Like, for example, these 4 corners have to be equal, but this only has to be equal to this. This only has to be equal to this, and this is equal to itself, so that's fine. It's just kind of casework. So now we want to make all values of x equal, and so there must be some like, let's consider like x1. Let's consider the 4 different values in this matrix. So let's say we have 2, 3, 5, and 7. I don't know. Some primes, why not? Then there must be some y such that all of these numbers will become y in the end. And we can both increase and decrease, meaning that for some y, the answer is the sum of like xi, or it's the sum of the absolute value of xi minus y. Since either you decrease or you increase to make xi equal to y as fast as possible. The values are up to 10 to the 9th, which means you can't necessarily try all possible values of y. But it's just like provable that the final value of y is going to be one of these array values. And in fact, I think it's the median. Like the median of the array is optimal enough. Because the way you can show it is like, say you have a number at 2. Then when you move it to 3, how do these costs change? So this cost increases by 1. This cost decreases by 1. And these costs decrease by 1. more specifically, when we're at some number here and we move it to the right, all the numbers to the right decrease their cost by 1 because they become closer, but all the numbers to the left increase their cost by 1 because they now become farther away. And so if we kind of plot out the cost as a function of y, we get sort of this, like, it's not a smooth curve, but it's shaped like this. And kind of the amount this changes as you go from this point to this point is equal to the number of elements to the right minus the number of elements equal to the left, and it's going to go down this much. And then this is going to go up this much by the number of elements on the left minus the number on the right. And so we want to kind of like find this bottom point. And R minus L and L minus R, I guess we can consider this to go down R minus L, but because R minus L is negative, it's actually going to go up. And so in some sort of like function analysis kind of thing, this is first going to be negative. Like the decrease is first going to be negative because you have more elements on the right than the left, but then once you hit a certain point, it's going to become positive. And so it's going to start increasing. And once it starts increasing, it never stops increasing. And once it stops decreasing, it's never going to start decreasing again. So we want to find the point where it stops decreasing because that's going to be the minimum. And that's the point where R minus L is equal to 0, which is the median. So it's kind of like a formal proofish sort of explanation of why it's the median. But it doesn't necessarily have to be the median. It can also be the array. It can also be an array element because there is an array element where R minus L is equal to 0. Specifically the one in like the middle. So basically on at least one of these array elements, R minus L is going to be equal to 0. And therefore the function is going to be at its minimum, which means we can just check all array elements. So kind of like that long-winded explanation basically shows that for candidate values of y, we can just check all possible array elements, or you can take the median. Median is probably easier, but I just wanted to be safe. So you can check all possible array elements and then take the sum. It's only like 4 squared because there are most 4 values. And then you do this for all kind of like groups of 4. Yeah, and then it's the sum over all of them because they're all independent. Okay, one final implementation detail is how do you find these groups of 4? Well, the way I did it was you can like iterate over the leftmost point in this group of 4. So you can iterate in the top left corner of the matrix. If you have an odd number of rows, then you do want to include the centers because otherwise you just won't include them at all, but you need to. So you include the centers, so in this case it's this. And then if something's, and then for some value, one value is the reverse in the row, another value is the reverse in the column, and the final value is the reverse in both the column and the row. So for odd values, if the reverse is equal to itself, then it's the same thing. So you might as well ignore it. And same here, this reverse is not equal to itself in the column, so you want to take that. But the reverse in the row is equal to itself. And over here, both the reverse in the row and the column are equal to themselves, so you don't take anything. And so you only have one array element, and obviously the cost is 0. So basically the condition is you only add this one to the array of things that you're solving for if the row reverse is not equal to itself, and this one if the column reverse is not equal to itself, and this one has to be if both of them are not equal to themselves. Because, for example, in this case, like there's no diagonal complement here. It's just because one of them is equal to the other, and the same for here. So the implementation is split into 2 parts, kind of finding these groups and then solving for them. And to find the groups, you take the kind of reverses, and then to solve for them, you just try all values of y as described below, as described before. That was long-winded. Jesus. Okay. Well, it is kind of a complicated problem, I would say. How many solves does it have? Not that many, so there's a steep difficulty drop from A to B. And then from B to C even more. C is just kind of annoying math bash, and I'm very disappointed that I somehow, again, I managed to submit something that would TLE. Like, I literally submitted the n squared thinking it would pass, but no, there's more you gotta do here. Let's consider the number 42069, just like a totally random number, right? And what we're going to do here is we're going to say, well, we have to consider the sum we get when we remove all subarrays. So let's fix the left point of the subarray. Then for this left point, we're going to kind of like solve for all right points simultaneously. Okay, arbitrarily, let's assume the left point is here. Now there are there are 4 possible things we can remove. We can remove this one, this one, this one, or this one. And we can't remove nothing, so this can't be here. Okay, so we remove this one. Then we're going to have some stuff on the left. For example, in this case, it's a 4. And then we're going to have some stuff on the right that we haven't removed. For example, 6, 9. And well, the basic idea is we can compute this left part and this right part separately, and then we just sum them together at the end. So what happens in the left part? Or actually, let's do the right part first. It's easier. So the right part is the sum of 9 plus the sum of it's the sum of the last character and then the sum of the last 2, so plus 6, 9. And then here it's plus 069. And here we have nothing, so it's like 0. And then we can't remove this one, so we can't have 2069. So the sum of these 4 values is just the total of the right values we get. So in general, for a prefix at position I, or for example, this is position 1, so it's before position 1, then you sum up the values of the suffixes of 2 to I, or 2 to n-1. Actually, it's 2 to n because you also kind of consider this empty thing as a suffix. Then 3 to n, then 4 to n, then 5 to n, or in all these cases n is 5. And then if we kind of move this left point over to the left one, then all of this stays the same, but we just get one more value. Specifically, we get the value 1 to n. So if we go along and we sweep this point to the left, or we can do it to the right, either way, it's just the sum over some suffix of values. And we can either do that with suffix sums directly, or we can kind of sweep this pointer across and just maintain the sum of this. And then to get the sum of this, we only have to add this one to the rest of these. I don't know what those letters are, but that's what it is. Now that handles the right part. And now we need to handle the left part. Oh, and to kind of compute these numbers, you can like 2069 is 2 times 10 to the 3rd plus 0 times 10 to the 2 plus 6 times 10 to the 1 plus 9 times 10 to the 0. So when you add some other number, then you're going to have 10 to the 4th. And you're going to add x times 10 to the 4th. So as you go along, you can maintain as well this running power of 10. And then you just multiply it by 10 and take it mod the whole time. And of course, remember to do everything like modulo 10 to the 9th plus 7. Otherwise, the number is going to explode. So that handles the right part. And again, the right part is this kind of like, if we choose this as the range, if we choose, say, this as the range to remove, then we get 4 on the left side and 6, 9 on the right side. So now we have to deal with these left parts. Let's undo. Oh boy. Oh boy. How far can we go? Damn it. Okay. I wanted to. Actually, I guess that's fine. I want to remove these. And that. And that. And that. Okay. So this is the left part now. How do we do the left part? So what happens here? We have 4 possible suffixes. And in the first one, it's 4, and we've already considered the right part, so we can just kind of do it, whatever. So the first one, it's 4. The second one, it's 4 plus x. The third, it's 4 plus xx, and like this one, it's 4. This one, it's 4 plus 6, 9, and the other one, it's 4069, which is 4xxx. So, in the same sense, it's 4 times 10 to the O, and then 4 times 10 to the 1, and then 4 times 10 to the 2, and 4 times 10 to the 3. And this goes up to n minus I minus 1. So it's the sum of 10 to the 0 plus dot 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 plus 10 to the, assuming 0 index here, n minus I minus 1, where this is 1. Because again, here we have 10 to the 0, here we have 10 to the 0, here we have 10 to the 1, here we have 10 to the 2, here we have 10 to the 3. Okay, but if we go along in the array like this backwards, then when we move this element over to here, the only thing that changes is now we get this as a power of 10, and this is 10 to the 4th. So only one thing is added, which is whatever number this is, maybe it can still be 4, times 10 to the 4th. So we can use, I think, the same running power of 10 that we used for the right side that we can for the left side. And in fact, I definitely overcomplicated this because I did the whole thing going forwards, which means that I use like suffix sums and stuff like that to be confusing for some reason. And it's just not necessary, really. What you can instead do is just move this over to the left starting from the end, and then you can maintain both the left and the right side sums that you need. So this product is 4 times this. So all you really need is these like prefix powers of 10s, 10 to the O plus 10 to the 1 plus 10 to the 2, all the way up to whatever you need. You can work out the indexing if it's kind of confusing. And then once you get that, you multiply that by whatever the number is on the right-hand side, which you also might need to be careful in keeping track of. For example, here it's not necessarily a single digit. If you have the right-hand side be right here, then the right-hand side is 420. Then like the right-hand side is 420, or the left-hand side is 420, which is clearly not a single digit. So in a sense, you also have to compute that in the same way that you compute these suffixes, where you can kind of, I think for this, you just need to do it like a prefix, where so if you have it like this, you have 420, then once you remove this one, or let's say you have 42, then when you stick on another digit x, the value of this gets multiplied by 10, and the value of x is x. So you get like 42, the previous value had, times 10 because you need to shift those by one place to the left, and then all that plus x, because x is the new digit you have in the ones position. So all this can either be done sort of like as you go or as pre-computation. And then once you do that, you consider all possible left endpoints and just like do all the sums out and add them all up, and then that's your answer. It's very, very ugly in my opinion. And Maybe there is a smoother way, but the way I came up with is a ton of math and you just kind of like bash out the indices and stuff. Probably better suited for an educational round, I guess. But whatever. It's fine, I suppose. How are we doing on system tests? Okay, we got A, B, and C. Nice. Okay, now for D. And D is... Okay, actually D I kind of like. That was cool. So you have a starting point, an end point, and a bunch of these like jump points. Where you can jump to some of these jump points if you have the same X or Y coordinate. Let's see, like right here. So now we can draw all these lines. It's gonna take a while because I drew too many points. Okay, I drew way too many points. We don't need all of these. Let's just use these four. But of course, we don't necessarily assume that the points are going to be like between the start and the end. They can always be on this side or wherever you want them to be, even like behind them. So don't necessarily assume that. Meaning that sometimes it is optimal to go backwards, like back one step so that you can get there faster later on. But anyway, we'll solve it for like without this kind of forward-backwards casework. It's relatively simple. When we draw all these coordinates, I don't know why I don't just do this. Seems easier. We can do the same thing here. I'm going to assume this is slightly above. Okay. So our path is either going to be just directly this, where we just Manhattan distance it up and go directly from the start point to the end point, or we go through some intermediate sequence of these jump points. Like, for example, we could go here, teleport down to here, then go here, teleport up to here for some reason. I don't know why we would, but we might. Then we can go up here, teleport over to here, and then just like do the thing and just go down and then be done. So our path can consist of possibly multiple jump points that we go through, and then the final distance is the distance from the final jump point we go to the end point. Okay, first observation, there's no reason to visit any jump point twice, because say you go here and then you take some like cycle or something and then you end up back here, but then you've like spent more time and you're no better off than you were before. So there's no reason to do that. Just kind of like basic shortest path arguments. And speaking of shortest path, one great way to do this would be to just model this as a Dijkstra problem, where to get from here to this jump point, the distance is the difference in x coordinates. And to get from here to this jump point here, the distance is also the difference in y coordinates, and we can go either way. And similarly here, we have these possible transitions to go from there to there, and same, we can go up here and over here. You can just take the minimum of the x and y transitions. It doesn't really matter. I don't think it makes a difference. But, yeah, we got D. Okay. So the key observation here is that, say you, you start here, right? Well, yes, you do start here. But actually, just say you're at some point here. Then say through some sequence of moves, you want to end up at this jump point. So either you'll go up in terms of x, go up in terms of y, or go through some other jump point. But what if we just like always assume you go through some... Actually, no, that's not necessarily true. But say you want to go through x, then we can say that this path is the same as going here, then teleporting down to this point, then going here, then teleporting up to that point through there. And even though that's, well, first of all, that's fine because teleportation costs nothing, but like what makes that kind of path cool is that if we're going to take some path through either x or y coordinates to get to some, say, x coordinate or some y coordinate, there's always an optimal solution where we instead go to the nearest jump point in terms of x, and then go from that jump point to maybe its nearest jump point, and go through some sequences of jumps all the way up to this. Now, why is that useful? Because if we're looking for the shortest path from start to finish, normally we would have to have an edge between all jump points in x and y directions. But since we only need to go to the nearest jump points in x and the nearest jump points in y, we only need to add an edge from this to these 4 jump points. Namely, the nearest ones in x and the nearest ones in y. If there's no nearest one, then there's just like no edge to add. You know? Okay, so that's like just it. Now, each jump point adds at most 4 edges, and of course we should have an edge from the start point to each jump point. Or we don't necessarily need to. The same thing holds true for the start point, but for implementation convenience, we can just have an edge from the start point to each jump point. And then we should have each jump point directly to the end point. Both of these costs are Manhattan distance, which is the difference in x plus the difference in y. Or I should say the absolute difference. Yeah, so essentially, that's just kind of it. So now we can basically just construct this graph like explicitly and then run Dijkstra on this graph. That's generally what I like to do for more complicated problems like these, instead of making some weird like BFS something. Essentially what you can do is, the steps of constructing this graph is as follows. First, construct an edge from every point, construct an edge from the beginning point to every jump point. The cost is the absolute difference in x, so like sx minus xi, and then plus the absolute difference in y, so sy minus yi. And then you can get from the start to any jump point. Now, in the same manner, construct an edge from every jump point to the end point. And the distance, the cost is the same, it's just the Manhattan distance, but this is fx, and this is fy. And also, don't forget that you can go direct, if there are no jump points, you can go directly to the end, or even if there are jump points. So in that case, the cost is just like sx minus fx, like the same distance in x and y. Okay, now that we've had all these edges, now the only edges we have left to add are edges between jump points. So this is simple. Sort these points by x. Assume they're sorted by x. Okay, cool. And you also have to maintain like their original indices or something, because you can't, like, you have to add the edge from the right values to the right values. Otherwise, it just wouldn't be the right thing. You would have some really weird graph that's not the same. You have to like have the original indices so that you can do that. But sort them by x, and then in terms of x, if there's a left neighbor, for each jump point, if there's a left neighbor, add an edge from the jump point to that left neighbor. And the cost is only the x distance, because you assume you're just going to jump by going to that x coordinate. So the path to get from this point to this point would just be to go from this to that x. So you can add an edge between this and then these two neighbors, the same thing. You can go through from here to here through this, and from here to here through this. Note that this should be a directed graph. Theoretically, I don't think it's... Actually, I don't think it matters if it's directed, but in terms of like the correctness of the graph, it should be directed. However, it doesn't matter if it's directed, because like, see, the issue is you can add this edge, but not this edge, because this isn't a jump point. Like, you can add this edge to here and go down to this jump point, but you can't go here. But the idea, I guess, is that you wouldn't want to go back here anyway, so you would never use the edges that aren't valid anyway. So you can theoretically make it undirected, but it doesn't matter. And then you add the edges from this one to the adjacent x values the same way, and this one to the adjacent x value. And then you just do the exact same thing for y. Sort the jump points by y, and then add the things to the adjacent y values. And the cost is just the absolute difference in y coordinates. So then here and here. Let me check my code to make sure, but I'm pretty sure that's it. Like, that's just, those are all the edges you need to add. So you do start to each point to end, start to end, and then points to points in both x and y directions. So here we go. We read in the input. Then we add an edge from start to each point. And actually, it would kind of be two edges from the start to each point. Either you can go in the x direction or the y direction. Although, in a sense, you can remove the y direction edge and just make it the minimum of the x distance and the y distance. I didn't do that. It doesn't really matter. Actually, sorry, this should be like here and here for more correctness to get to this point. But yeah. So add an edge for x and y, or just both at the same time. Then add an edge from each endpoint to the, or each jump point to the endpoint, which is Manhattan distance, the cost. And then add an edge between adjacent x's, and then add an edge between adjacent y's, run Dijkstra, and print the distance. And so my trick for sorting by y is that I had pairs of x and y. And so you can sort them by x easily because C++ just lets you do that. But then what you can do is, to sort by y, is swap all of the x and y values, then sort, then return them to x and y. And then now they'll be sorted by y because you sorted them when the y value is in the first position. It's just kind of an implementation trick. Not very necessary. And you can write a custom comparator too. It doesn't really matter what you do. But anyway, that is D. Okay, let me see if my E passed. Does it fail system tests? Oh, it actually does. Nice. Okay. Well, in that case, wow, there are a lot of sys-test fails on this. Wrong answer, 46. Yeah, that one got hacked. That one got TLE. Yeah, that's fair. How did other people do then? Wow, my rank actually didn't go down that much, even despite failing E. So then how many people have solved E? Or wait, that's not good. 47 solves on E. I guess some of them are upsolves. Jesus Christ, that is so many sys-test fails. How? Yeah, I guessed that these pre-tests should have been stronger because maybe these were hack cases actually. That might have been it, that the hacks were added to the pre-tests and that the system tests just ended up being terrible. Because for a problem like this where there are so many cases, just random tests are just not going to work. 42, 46, 46, 46, 46, 46, yep, 46, 46, 46. Okay, let's see what this test is. Is there anything special about it? First lines differ. Expected 510, found 526. So I guess we can make it better. There's no way that's a hack case. What was the case that hacked, like this guy, for example? Can we see the hacks now? Yeah, it's like a very small case. So that's A, that's BA, that's... Is this something I do? No, that guy has it shorter, so it's like a bug that passes pretests. Okay, well, I don't know what's up with that, but Maybe it's wrong, maybe it's just an implementation bug. What did other people do? Did they do something similar, or did they like do smarter things? It's almost the same thing. Actually, I don't even know. He does... I'm not sure. Slightly weird. How many points do we have for that? Not that many. So I think he must have... How did that work out? Because I was ahead of him before, but he must have like had more points on that or something. Alright, well, I don't know what to do now. I guess I'll just go over my idea, and maybe it's wrong, maybe it's not. But I will, if my idea ended up being wrong, I'll put in the title like it's only solutions for A to D. And otherwise, if it's right and it's just some implementation bug, I'll just like put in the description, call the title A to E, and call it a day. But the idea is basically, and also I don't have an idea for F, so I'm just gonna like leave it. Yeah, okay, I'm not really sure what to do about that. But let's say, here's my idea for E. You have some string. Let's say, for example, the string. And so the idea I had, which is kind of greedy and probably is wrong, actually, is that if you have some pair, consider the end of a string as like some magic character that's less than all lowercase letters. So let's call it like a star, for example. And we'll say that like a star is better than any character with a star on the end. So star is less than a star. Then the idea behind this is that then the idea behind this is that you only want to like remove a pair if it will give you like a better chance in the future to... I think you kind of only remove a pair if it moves the star close to the character. So like consider some suffix that's kind of like here. You'll want to remove this pair only if, I guess, this character is less than this one. That's the basic idea, and there's a lot of casework and implementation to work out in that. Kind of don't know how to explain my implementation, so I guess you can check my code. Basically, the trouble with this implementation is that you could potentially have some other pairs, say like E and F. Wait. Could potentially have some other pairs like E and FF over here. And you could have removed these already, which means that you can't compare it to only the string. You have to compare it to like the best that you have. I'm wondering, it might just be as simple as like checking the character in the second, like in the position 2 characters after what you're currently at. Oh, and also we're constructing the string backwards because we'll kind of just do that. And then to answer the problem, we have the string at all points in time, so we can find its length and then check if its length is the best. Or we can check if its length is greater than 10. If so, we can print like the characters. And so I use a deck for that because it allows you to like push to the front and the back and also random access, which is exactly what we need. We don't actually need the back, but using only a stack, I don't think it offers random access. I don't know, maybe it does, but it doesn't really matter. Decks are fine. So we only remove this if removing it will move this like closer to the front. Which means that if this character is worse, say this character is like H or something, then we don't want to move H closer to the front. We already have D here, which is better than H. And yeah, I guess that's the idea. And then there's a lot of weird implementation stuff going on with that. I'm really not sure if it's just a bug that I have or it's that this is actually wrong. Because it seems like that's what the other accepted solutions were doing, kind of a greedy, although I'm not sure. Maybe it wasn't. So for now, I will verify if this idea is right later. But the basic idea is you only remove a pair if the rest of the suffix that you now shift over to this location by 2 characters is strictly or is better. And in terms of length, you can handle making it shorter by sticking the star character at the end, and that will like deal with it. Okay, I guess that's it. After this video, I'll try and change up my implementation and make it better. But in any case, that is the idea. So, and then it's just greedy, and if so, you remove both of these characters and you continue on the suffix. Okay, and F, I have no idea what I'm doing at all. Yeah, no idea what I'm doing. So, we'll leave it at that. So A to D for now, maybe A to E later. Okay, that was the screencast. Hope you enjoyed. Goodbye.